So we are going to be looking at something called the iceberg exercise. The actual description of this exercise is available on our homepage under the publications section. So if you go to the publications and a little bit down, you can find the iceberg exercise. It's a PDF document that outlines the requirements for building an iceberg tracking and drift prediction system. And we created this example to showcase features in anchor modeling. So if you look at this, the objective is to track and predict the movements of icebergs. And the way this is done, the solution here, is that you actually put GPS transmitters on the icebergs and attach them to the iceberg. You do this before the iceberg has shelved off into the water, so you do it on the actual glacier or whatever is forming the icebergs. And then when the transmitter starts moving, then you know that the iceberg is adrift. So that's a very brief explanation of what this is supposed to do. And of course, we also want to showcase something we call positors in anchor modeling, so you can have concurrent views and possibly conflicting ones as well. So we also want to capture data from boats that may happen to see an iceberg that they're passing by, and maybe they can give a better location or a better estimate of the size or something like that when they pass it. So you can read this in detail if you want to before looking further at this video in order to understand all of it. But I think we should move on to actually looking at the model. So going back to, I'm going to keep that one, to Anchor Modeling, the home page, you can click on the online modeler, the test version of it. And it's going to load some model here. I think this is the retail one, so I'm going to load another model. Load public model from cloud. We have made this iceberg model publicly available. So if I type iceberg here in the search filter and click search, you will find the iceberg exercise. So I'm going to click this one. I'm going to accept the changes it wants to make. Switch on some names here and toggle mnemonics so it's easier to read. I think I'm going to zoom in a little bit so we can get it better on screen. So this is what the model looks like, and what you can see here is that we have two anchors. We have the transmitters and we have the icebergs. And in order to capture the fact that how these transmitters are attached and to what icebergs, there's a tie here that represents this attachment relationship. And of course, a transmitter doesn't need to be attached at all times. They can fall off, for example. So we need to have a knot here on the tie that represents whether or not this is attached currently or if it's not attached. Icebergs can split and merge. This is also one of the requirements to keep track of these. We also wanted to keep track of certain areas that icebergs will enter. So this is actual entering of an area. We can also predict some places that that the icebergs are going to be. So we have another tie here, which is the areas where it's expected to enter or exit. We also have other attributes on the iceberg. We keep track of when the iceberg was formed, when it disintegrated, the size, and size is of course historized because the icebergs melt over time. Whether or not it's frozen, that means if it's stuck to the seabed, it can start moving and then stop again. The actual location right now, and whether or not it's submerged. And as you can see, the small I here says that this is an idempotent attribute. That means that if I try to enter a new value for submerged, if I try to enter the same value for submerged, with a later time point, it won't store this because it's not a change. That's what idempotent means. Here we have the transmitter. It also has a few attributes. When we first receive the signal from the transmitter, so we know that it's alive. The last signal, well, the first one, that's something that it's not expected to change. Once you've received the first signal, it's always going to be the first signal, the time of the first signal. But the last signal, that's always going to change. So for every whatever granularity you have here, day or hourly or something like that, this is going to change over time. Whether or not this transmitter is missing in action, and the location of the actual transmitter as well, because this location could be assumed to be some sort of average of the different positions of the transmitters that are attached to the iceberg. So this is what the model looks like, and I'm going to generate the SQL code for the model, and we're going to implement this in a database. So I'm going to select everything, copy, and move over to a remote desktop here where we have the a database. We haven't created the database yet, so I'm going to start by actually creating something that can hold this. So let's call it Icebergs, and let's connect this one. Oh, it was already there. We needed to change the database to Icebergs. I'm going to run the script that now implements this model into the database. So now we have the model in the database. We have also prepared some queries, and these queries are also available, as you can see in the post here later. You can get this script. So the first thing I'm going to do is to change to the correct database. Then I'm going to create one more positor. To begin with, we have one positor created with identity 0. This is sort of the default positor. But in this case, I also want to model that a boat will see one of the icebergs and report its location. So I'm going to execute here to get one more positor, meaning that now we have two positors, 0 and 1. In the model, you have some different knots. Usually you populate these first with different values. So I'm going to run these queries that populates the knots with their values, whether or not an iceberg is submerged, for example. Then I'm going to move further down. We're going to insert a signal from one of the transmitters into the transmitter anchor. And now we're using the latest view of the transmitter when we do this insert. And the reason for this is that the triggers that we have instead of insert triggers are created on the latest view. So in this case, this will behave like an insert into a table, but it's actually an insert into a view that splits this insert into many inserts into all the underlying tables that we have in the model. So the transmitter, there's a number of different attributes I need to populate. First, I'm going to indicate which positor am I inserting this as. So I'm using the default positor in this case. When did this data change or become known? When did we actually insert this or make this statement? We call this the combination of a changing time for an instance with the value we call posit, and we have something called a positor, and the posited at is when does this positor make this statement. And this positor is making this statement on the 1st of January 2015. So on this date, this positor 0 is saying that the location here, which I'm specifying here, was at this point in time, this location, with some reliability as well. So I'm going to say here that we're not 100% sure about this. We're like 50% sure that this was the location. Missing in action, it's not missing in action, so we know where the transmitter is. The first signal was received on the 1st of April in 1912. And the last signal that we have, at least on the 15th, is at 20 minutes to midnight. So I'm going to insert this into the transmitter there, and we will hopefully get some data in the transmitter. Now I'm going to make an update, and updates are possible for historized attributes. So looking at the model again, we can update location, submerged, frozen. We cannot update the formation date or disintegration date. So what I'm going to do here is to update and say that the last signal is on the 16th, the day after, received at 1 minute past 1 in the morning. We're 80% sure about this, and we're actually stating this on the very same day that we stated the facts above. So this update will also insert data, and in Anchor modeling, data is never destroyed, so we get a new row in the database here. That's the effect of the update. So there's an instead of update trigger here on this view that takes care of the underlying logic. Now if we check the data, let's say we look first at when was the last signal received on the 15th. So here we're going to use something called the point-in-time view of the transmitter. So let's see. Let's run both of them on the 15th and on the 16th. So here you can see that on the 15th, the last signal was received at 20 minutes to midnight, and on the 16th it was 1 minute past 1 in the morning, just as we expected. So the point-in-time view allows you to travel in time over changing time. Now these changes are normal changes that we're expected to have in the data that we're looking at. However, there are also other types of changes, and those types are corrections. That's when something entered the database that was erroneous. There was something wrong with the data. So in this case, what we do here is to actually clear out that which was wrong. So let's say that there was something wrong with the first signal here. So we set the reliability to 0 for this particular posit. And then we insert a new one, a new posit, stating that the first signal, it was not in fact received on the 1st of April, it was actually received on the 2nd of April. So here we're making a correction of existing data, and a correction is always made by first canceling out the previous information that was erroneous, and in that case we use the reliability and set it to 0. And we enter some new information that we believe in instead. And in this case we're 80% sure it was on the 2nd. So I'm going to run this query as well. Okay. And now let's look at the data. Now I'm going to use a more advanced function here. So this is not just the changing point in time. This one actually takes the bitemporal point in time. It has both changing time and positing time. So as you can see here, the positing time here for the second statement is the day after. Oops, I don't think that matters. That was a little bit of an error there. Okay, so let's look here. On the 31st of December, that's actually before I made any posits, meaning that we shouldn't see anything at that date. On this date, the first, we should see the uncorrected value, and on the second, we should see the, no, that was actually correct, sorry. It's when I actually set this reliability to 0. So, okay, let's run these. So, as we expect here, you can see that the first signal, as we knew it, we didn't know anything about it on the 31st of December. On the 1st of January, we thought it was the 1st of April, and here we changed our mind. We corrected it to the 2nd of April. All right, so let's move on and create an iceberg as well. So I'm going to execute this, and we get some information about an iceberg. It's not frozen, it has a location, it's not submerged, it has a specific size, and the disintegration date is null. So we could either we could just leave out this part of the insert, or if we insert a null value, nothing will happen, because in anchor modeling, null values are not stored. It's just the absence of a row in the corresponding attribute table. So now let's also have this boat that sees the same iceberg. So the difference here is that in this case I don't provide an iceberg identity. There's no IB ID here, meaning that this first query will actually create an iceberg with identity 1. So in this case, if this boat wants to talk about the same iceberg, I provide the iceberg ID here and say that I'm talking about iceberg 1. And in this case, the boat has a little bit of a difference of opinion here, because the boat actually states that this iceberg looks like it's frozen to the seabed. It also has a little bit of a difference in the geography here, so it believes that the location is slightly different from what the transmitters have been stating. It's not submerged, and it's also quite much larger than the prediction model would have stated. And it's not disintegrated because we're actually seeing it. So let's look at the data. We will first look at the icebergs and the difference in opinion now between the two different positors. So if I execute this query, oh, maybe I didn't run the query above, sorry. Okay, so here's the boat. Now there should be some data for positor number 1 as well. So here we are. So here you can see the differences listed. Positor 0, which is our prediction system, believes that the size is 555 square feet, but this one says it's 911 square feet. And it's not frozen or frozen. The boat has probably a better idea about the states, since it's actually doing a visual on this one. And then you have the actual locations. It's easier to see this in the spatial results. So here you can actually see that this is what the boat is seeing, a slightly larger iceberg in this location, and this is what the system is predicting, that the iceberg should be there and smaller. So now let us insert something into the tie as well, because right now we just have the transmitters and the icebergs. We haven't really connected them in our data. So I'm going to attach our only iceberg to our only transmitter, and it's currently attached. and we believe that it became attached on the 13th of February, and we're stating this on the 1st of January 2015. So I'm going to execute this. Now we also have a row attaching this one to that one. So I'm going to look now at the data by joining the icebergs with the transmitter that it has. And now I'm going to start by using the latest view, has a small L in front of it, for all of the different tables that are involved here. So in this case, if I run this query, we will see the information as it is, given the latest information that we have, both with respect to changing time and positing time. So in this case, this behaves exactly like a regular non-temporal database. This is what you would see if updates and corrections were to destroy the old data, so you only have the latest information available in the database. So in this case, you can see that we have two positors with a lot of different information. Of course, difference of opinion about these two icebergs. If we go further here, and that's why I'm doing the left joins, you will see that at the end here, there's no information available about the transmitter for the second positor. And that's because it's only our prediction system, positor number 0, that has any concept of transmitters. The boats just see icebergs and reports information about icebergs. So we cannot expect positor 1 to know anything about the transmitters. Now let's move on to a slightly more complex join here. In this case, we actually make use of the fact that we have history in an anchor model. So here we want to see what did the information look like at a certain point in time. So again, we can use this point in time view that takes us changing time and travel back to that point in time and see what the information looked like then. So this is exactly the same query, but run as it would have run on the 13th of February, or what the data looked like on the 13th of February 1912. So again, you see we get the same two rows, but there will be a few differences here in the data since we moved back in time. So looking at these two SQL queries, you can see that there's not much difference. It has exactly the same structure. The only difference is that we send in a parameter to all of these tables, and this type of join is called a temporally independent join, because what we can do here is that we can first sort of rewind this table back to this date, rewind that one and rewind that one, then we produce the join afterwards. So when you can do that type of sort of move back to a certain snapshot before doing the join, you call the query or the actual join temporally independent. And this actually covers most use cases that you have within temporal data, that you actually first you want to move back to a certain point in time and see what data look like at that point in time, one specific point. But there is also another type of use case which requires something called a temporally dependent join. Say instead that if looking at the previous query here, where were the icebergs and the attached transmitters on the 13th of February 1912, the date that we want to look at? Slightly different query that requires a temporally dependent join is where were the iceberg and attached transmitters at the time of the formation of the iceberg? All of a sudden we have a dependency on another point in time when the iceberg was formed. So this becomes a little bit more complicated, but it can still be resolved set-based by using the apply operator that you have in, well, among other databases, SQL Server. So what we do here is we find first all the formation dates that we have for the different icebergs. Then we pick up, using the point-in-time function, what did this iceberg look like at the time of formation. So this will actually fetch the iceberg as it looked like at that point in time. So in the apply, we do the actual join. So that was previously join conditions on in the on section is now here in a where statement within the apply. And here you can see we want to see the attachment at the time of formation, and we also want to see what the transmitter looked like at the time of formation. So this query, very similar result as the previous one, but using a temporally dependent join instead. So slightly bit more code, but still quite a simple way to actually do a complicated temporal query. So let's move on. We can also add bitemporality. Up until now, when we did the joins, it was only over changing time. But of course, we have 2 points in time now. We have changing time when things changed in the domain that we're modeling, and we have the other positing time, which is when we made corrections or had a different opinion about how reliable the information is. So in this case, we will create a bitemporal dependent-independent join. So we have the same dependent query as we had previously, where we depended on the formation date of the iceberg, but we're independent over the positing time. We want to see the information as it was posited on this date. So what did we know with respect to all the information on the 1st of January? So here I'm going to use this more complicated or advanced time traveling function, in which I specify a positor, a formation date, and a positing time point. So I can create a variable that holds this time point and use the same time point in all of these places, meaning that this is independent, whereas this one, which is different for every iceberg, produces the dependent part of the query. So this is bitemporal, you have 1 and 2 time points. So running this query will also produce a very similar result. So this is the information about what the icebergs looked like when they were formed, given what we had said about it on the 1st of January 2015, which is the positing time point. So slightly more complex query, but still quite easy syntax for such an advanced temporal query. And finally, we will create the bitemporally dependent join. So we will have dependency both on changing time and positing time in this query. So the added condition here is that we take the positing time for the formation date and use that as the dependency over positing time. So basically, we look at the information or the icebergs as they looked when they were formed, and given the information we knew on the date that we posited that formation date. So instead of using the variable I had earlier, which was a fixed value, I used this posited at value from the formation date attribute. So this is the dependent query. and running that also produces the same or similar result. This is quite a complex bitemporal query, including a bitemporal join dependent over both changing time and positing time. And looking at it from two different perspectives, we have two positors here, 0 and 1. So it's concurrency as well in this example. This sort of mostly captures all of the features that I can showcase when it comes to concurrent reliance temporal anchor modeling. What we didn't look at is the reliability. We could have in each of these queries added a condition stating that we were interested in only information above a certain reliability as well. But you can figure all of that out as an extended exercise. All right, thank you, and thanks for watching this.